here we're going to talk a little bit about inflation. Now, inflation is a rise in prices from a given base year. And inflation is given by a rate. The annual rate of inflation, which we'll call lowercase a, is that additional proportionate cost 1 year later. So if an annual inflation rate is 2%, then a good that costs $1 in a base year will cost $1 plus 2%, so $1 and 2. So goods that cost $1 in the base year cost 1 plus A, where A is written in its decimal form. 1 plus A dollars 1 year later. Now, when inflation is constant, which is not necessarily the case, but we will assume for our examples, inflation is constant throughout the year. But when inflation is constant, we can use the compound interest formula to measure inflation. So let's write that as a remark. Remark. When inflation is constant, we'll assume constant across whatever time period we're considering. When inflation is constant, we can use, I should spell use right, and I should spell can right while I'm at it. We can use the compound interest formula to measure inflation across a given time period. Maybe I should say it the way I wrote in my notes. We can use the compound interest formula to project prices. That's a better way of saying it. So if we know that inflation is constant across, say, 5 years, we can use the compound interest formula to find how much something costs 5 years later. And how would that look? Well, A would equal P times 1 plus, here our rate is A over M to the MT. But inflation is not compounded several times a year. It's constant across we're assuming it's constant across the years. So here, the number of compounding periods is 1. So you just get P times 1 plus A all to the T. Now, let's do an example. But before we do the example, why can the compound interest formula be used to measure inflation? So why not the simple interest? Why the compound interest formula? While you're pondering that, I will write an example. So the question was, why do we use compound interest instead of simple interest? Well, say we're measuring inflation across 5 years, and say it's 2% per year, as we have here. But say it's 2% per year. Well, that doesn't mean in the first year it gains 2 cents, and then in the next year it gains 2 cents. That means in the first year it gains 2 cents, and then with that remark that I erased, the product costs $1.02 at the beginning of the next year. The inflation, the next 2% would occur on that $1.02, not the original dollar. So we use the compound interest formula to project the prices. So this doesn't mean across, so to illustrate that further, this example, suppose there's constant 2% inflation across 5 years. What is the projected item or cost price of an item that costs $100 in the base year? This does not mean 2% of 100 is 2, so this does not mean the price is $110 because it's $2 for 5 years. This means 1 year later in 2016, it's $102. 2 years later, it's a little more than $104. And we can use this formula, to figure out what the projected price is. So let's say A equals the base, which is 100, times 1 plus the annual rate of inflation, 0.02, all to the 5. And what does this equal? This is about $110.41. Now, given this information about inflation, $100 buys some product in 2015. But that $100 does not buy the same product in 2020. In other words, this $100 becomes worth a little less in these 5 years because of inflation. And we can use inflation to come up with a formula that shows how the dollar loses value. So let's do that now. The purchasing power of a dollar 1 year from now relative today, given inflation, annual inflation rate A, is given by, well, it's given by a ratio for starters. But which one? Well, it's worth $1 today, or what? It's worth $1. Let's say today. And in 1 year, we had that remark that said a dollar would then a good that costs $1 would then cost 1 plus A dollars. So today it's worth $1, and today a good would cost $1. Next year a good would cost 1 plus A dollars. So this ratio would give us the purchasing power of $1 1 year from now, given an inflation rate. Now, this fraction actually reduces, and we will use the reduced fraction. You don't have to use the reduced fraction, but it is useful for a couple things. So it would be 1 minus A over 1 plus A. That's an A. These are all lowercase a's. There are no 9s around here. Why does this fraction equal that? Well, you can just combine the fractions, get a common denominator over here, and what would you get? You'd get 1 plus A over 1 plus A minus A over 1 plus A, getting the common denominator, and this equals 1 plus A minus A over 1 plus A, and then that numerator simplifies to just 1. So we will use, you could use either formula you want. That, I guess the first one is easier. It's easier to substitute if you're given just an example as for this. But this second one is nice, I think, because it shows you how the dollar is getting less valuable given an inflation rate. So this right here, I'll remark that this behaves like a negative interest rate on the dollar. So this is just 1 year from now. Well, it behaves like a negative interest rate on the dollar, so with that negative interest rate, with annual compounding, I should say, on the dollar, so with that we can find the purchasing power of a dollar T years from now. So let's write that just here. The purchasing power of a dollar T years, or maybe we only have to do $1. The purchasing power of P dollars T years from now, relative to today, given annual inflation rate A, is given by, well, we would just use this formula. So that first one gave us 1 year from now. but it behaves like a negative interest rate. So we can apply that to the compound interest formula. So we'll say A equals what? P times 1 minus A over 1 plus A, all to the t. So we have P times how the dollar is devaluing at a certain rate, and that happens each year. So let's look at an example. I have an example on this side. Example. So here we'll substitute A equals P, which is, well, we're starting with just one 2015 dollar. So 1 times 1 minus A, 25%, over 1 plus 0.25, 25%, to the 4th power. And this is approximately equal to $0.41, also known as 41 cents. So if we have 25% inflation, well, a dollar in 4 years loses more than half of its value. So you can see just from that, it's very common to think high inflation is quite dangerous. Let's look at a slightly more realistic example. What if we changed this to 3% annual inflation? So I was going to rewrite the question, but why do that when I can just erase 2 numbers and replace it with 1 number? Well, I guess I have to replace these other numbers. Suppose there's 3% annual inflation, which I'm also pretty sure is not realistic. I actually don't know what our inflation rate is in the past few years. But suppose there's 3% annual inflation, what would the value be? Well, here, A would be 0.03, and it would be a slightly different devaluing of the dollar. The dollar would then be worth 89 cents after 4 years. So I'd like to make one more observation about this example with 25% annual inflation. This example is more illustrative than the 3% for what I'm about to explain. 25% annual inflation. In 1 year, that does not mean the dollar is worth 75 cents. It actually means the dollar is worth 80 cents. And where did I come up with 80 cents? Well, let's look at this example. 25% annual inflation from 2015 to 16. What would the value of one 2015 dollar be in 2016? Well, it would be A equals 1 times 1 plus, or minus, not plus. It's negative because inflation causes the dollar to lose value. Negative 0.25 over 1 plus 0.25, in this case raised to the 1st power, equals 1. 0.25 divided by 5 quarters. 1 quarter divided by 5 quarters is 1/5. 1 minus a 1/5, which equals exactly 80 cents. So here, the 25% inflation rate doesn't mean it loses 25 cents per year. It's actually losing 20 cents per year. And we can see that losing 20 cents, maybe I should write that as 0.20. 1 times 1 minus 0.20. This value right here, this fraction, this A over 1 plus A, shows, I just wrote shows, S-H-O-W-H. That was because the next word I was going to write starts with H. Shows how the dollar depreciates across a year. So this rate shows how the dollar depreciates, and in general, this formula, A equals P times 1 minus A over 1 plus A, or 1 minus a depreciation rate can be used in examples of using things that depreciate, like a car, for example, depreciates. A piece of equipment, for example, depreciates. So let's look at just one last example of a car. You buy a car in 2015 for $12,000, and its value depreciates at what? At 15% per year. How much is the car worth in 2018 dollars? Well, here we're already given, in this case, a 15% depreciation rate. So we're already given what this fraction would simplify to if we had a value A. We're not given a value A here. We're given a depreciation rate. So here, I'll still use a capital A. We start with $12,000, and it depreciates at 15% per year. So that's 0.15, so we take 1 minus 15, and it's across, what, 3 years? And this is approximately equal to 73.69 and 50 cents. So that dollar depreciating idea extends to all types of depreciation. And of course, another way of saying this is that each year the car is worth, what, 85% of its initial value. Each year a dollar is worth 80% of its initial value, but we find it more convenient to describe it as starting at a 1 and then having some sort of rate of depreciation. So try the examples with inflation. There are a few types of questions you could be asked on inflation.